Okay, so we're reaching the end of this section. Very long section, stability. Quite complex. A lot of what you've seen in this section is stuff that a lot of is self-developed. So I think it's a very interesting part of this section, the part that I do the analytical analysis, because it's you won't find it anywhere else, and you can feel the equations much more than if you don't do some simplifications and you don't play around with them. Uh, we concluded very interesting things like the tendency of long vehicles, tendency of long rockets to pitch roll coupling, which is the nightmare everyone has, and more after seeing problems Dare had with Stratus 2 and Stratus 3, and hopefully they don't have in Stratus 4. I think I was checking their design review of, I think it was Stratus 4. They thought maybe it's because it's the length to the ratio, but as we saw in our equations, L to D ratio doesn't appear at all. What appears is the length, the absolute length, not this non-dimensional number. We remember that the natural frequency, well, it depends on 1 over L, the velocity, and then the specific span, and well, the center of gravity, non-dimensional, the length of the nose, but we don't have the diameter anywhere. It's buried inside here, but it's not the it's the specific span. So, and as you can see, I haven't talked about many parameters related to the fins. So we only have specific span, and sometimes only at Mach numbers above Mach linear. We talk about the how did we call this? The specific mean chord. But in the rest of the geometry parameters, well, I haven't even introduced them to you. The sweep angle, the taper ratio. Well, taper ratio is kind of inside here. But yeah, all these angles are going to be important for other stuff. The sweep angle, but what's important for stability is actually the span. Interestingly, so yeah, we talk about how to prevent pitch roll coupling, and why probably Stratus 3 failed and Stratus 2 was just about to fail, and I think they weren't so open about Stratus 2, what happened to it, but yeah, my guess again is pretty near unstable vehicle. Hopefully it didn't blow up that time, but yeah, it had the same problem. Very long vehicle, low resonance frequency. So what else have we talked about? We talk about modeling all the aerodynamics which are relevant to stability. So the aerodynamic center, the normal force coefficient, and yeah, I've put a lot of emphasis on pitch roll coupling. Yeah, pitch roll coupling is a big issue, and as you know, I mostly improvise these videos a bit, and getting back some old notes and recalculating stuff just in case I didn't mess up. But it's a nice time to do a quick reread on the on the subject. And I was reading, for example, I came across with a nice article which talked about mitigating roll lock-in, which is basically pitch roll coupling. As you can see, the math, the physics here is much more complex than the one I presented to you, but still, the one I presented to you for starting out, it's good enough. And if you're interested, there's always going to be more information. But yeah, it has a nice conclusion here. This is, by the way, a paper from 2015 or so, and basically the recommendation is very, I like it because it's super clear. To improve resistance to roll locking, consider using standard margins of greater than 2 calibers and more than 4 fins. So basically the conclusion is, adding 5 from 3 to 4 fins. It doesn't get much better in terms of preventing to pitch roll coupling, but from 5 to 6 and up to 8, it improves a lot. So typically all sounding rockets have been 4 fins mostly, some of 3 fins, but it's really it's not. I haven't seen many sounding rockets that have more than 4 fins, but there are definitely a lot of missiles that have 8 fins. I think mortars have 8 fins as well. So yeah, that's a nice thing to note. And I came across with another article which was from INTA. Yeah, INTA, which is like the Spanish Aerospace Institute. It talks about pitch roll coupling as well. It's nice to see, a few conclusions that I had. Well, the article shares them. It's nice to see this. So as you can see, this is the natural frequency of the rocket in function of time. I guess this should be time. Yeah, time of flight. It grows pretty linearly as we could expect. And then here, what's plotted here is the roll rate. So what it says is that if you're always going to have a roll on your rocket, and if you don't control it, it's going to blow up because you don't know at which pace it's going to roll. Okay. So what they did in Spain and the rest of the world is given it a cant angle in the fins, so they could model properly, more or less the roll rate. And what it says is, if you pass, this is the resonance point when the two frequencies meet. But if you pass quickly this point, resonance doesn't have time to do its effects, so you're good. So that's what I told you about Rexus in a few videos before, if you remember. I told you that you're gonna have to pass a point in which the two frequencies are gonna meet, but if you blast through it, then you don't care. So it's nice to see as well this this graphic. So by the way, I haven't talked about the relationships, kind of the role dynamics. I haven't talked about the the roll moment induced by counting of fins and the damping and all that. I'll just leave you here the reference if you want to read about it. I think the most important part, which is like all this discussion, you have it here. If you want to get the numbers, just go to the Open Rocket technical documentation. You can find info here. It's a very nice document. Yeah, he took a lot of time to get all that information together. Yeah, so you can. This is for, let's say, roll moment. Okay. So what else? Let me think. Yeah, I'm just gonna place some more references. I've talked about them through the videos, but here you can have them. You can have them together. So this is a nice document. Maybe it's not comprehensive. It has a few gaps, but it's nice to. It's very precise, actually. I think I talked about this before. Its models are surprisingly precise for the application it has. I mean, its expressions are way more precise than the book from Fleeman, which remember is the book I based all the aerodynamics modeling. Fleeman is the author. Then the book is Missile Design, I think. Oops. And Systems Engineering. I think this is the last version, but he has previous versions of this book, which I think it's called Tactical Missile Design. So maybe this is the third or fourth version of the same books. I think this book is from like 2015, and yeah, he does like a new book every 4 or 5 years. Like he just improves this book. So the first book has maybe a couple of 100 pages. The last book is like 800 pages. Has a lot of information. So yeah, I found this really interesting and nice to start with, for the aerodynamics. But it supposes quite a lot about general rocket stability. And so my favorite is Mandel's book, which is Topics on Advanced Model Rocketry. I love the care they took to write all this book and get it done at such quality and with such mathematical rigor and and the application was just to throw small model rockets to 100 meters, but still the math he developed and is awesome. I haven't found anything like this book, which talk about linearizing the equations, and it's great. It's a great book. So definitely start with here if you're pretty lost. It's a great book to start with. It's I think the best first book to start with if you wanna know about rockets. then move maybe to Fleaman, and then Open Rocket. Open Rocket is pretty, it supposes that you know your stuff, I guess. Except maybe the first chapter, it's more slow mode. But then I think he thought, well, I can't just explain everything, so I'm just gonna get to the point and put out the equations, I guess. So yeah, and then of course there's tons of papers and a lot of stuff out there. The problem is that there's too much stuff out there. So you're gonna find a lot of information which is not organized, not in the, it's the amount of information is never gonna be a problem. The problem is if you're ready to digest that information, if that's gonna be useful for you, if that or if it's just too if it's too easy. So yeah, you gotta be patient, but hopefully all these videos it's gonna be a really big shortcut for you, hopefully. So at least you know where to start. You already know a lot about stability if you finish this series. I haven't gone through everything. I would have taken forever. I already taken forever to finish this section. I still have a lot to go. So yeah, definitely I can't go in much more depth than I've gone in this section. But I think you have all the tools for understanding, stability. And yeah, I definitely think that the most valuable thing that I can offer you is all these comments, and all these, these conclusions about, well, what affects pitch roll coupling, what is good for this, what is, more practical information you're not going to find explicitly anywhere else. Yeah, because it takes a little bit of reasoning and looking at the equation, giving it a couple of thoughts. So yeah, hopefully you've liked stability. I love this part of the design. So the rest of the sections on airframe design, I'm not going to go in so deeply. Maybe I'm going to... Well, I have to talk about drag. Drag is going to be fast. It's just, putting out a lot of equations, and yeah, there's nothing much to it. And then what else in airframe design? Well, we have to talk about... I'll go quickly through a little bit of structures. Maybe I'll talk about materials. Maybe I'll talk about aerodynamic heating. I have to talk about, definitely. That's a big issue. So I remember this. I talked with this group of students. Can't remember, maybe from Austria or so. They were trying to do a supersonic rocket that was reaching, 50 kilometers, something like that. Double stage, but commercial off the shelf. So they didn't do any motors or anything, so they had to do the airframe. And well, the first thing I asked is, well, oops, it's buggy. Yeah. Well, what are you gonna make the airframe from? Well, aluminium or something like that. Well, what velocity is it gonna reach? Well, Mach 3 or so. Well, you're gonna melt aluminium at that those speeds. That's the first thing you have to look into. Aerodynamic heating. So yeah, and they weren't aware of that. So yeah, I have to talk about aerodynamic heating. That's going to be a big issue for bigger rockets. It's going to be negligible if you're not hitting, Mach above 1, 2. Well, yeah, above 1 point something or 2 is going to be negligible. But yeah, for larger rockets, It's going to be inevitable to, to encounter error heating. So yeah. If you have any comments, as always, you can drop me an email. That's my surname, but kind of funnily written out. Yeah, see you in the next section, still in airframe design. We're going to talk about drag next, maybe. Yeah.